BC Calculus, lesson 11.3, polar functions. I look at polar coordinates, they remind me of parametric equations. They actually are a parametric equation. We'll show that in a little bit. But they just open up this incredible new mathematical way to look at the world. Polar coordinates work on a radius and an angle. The angle should always be given in radians, but you'll see we do it in degrees here and there. Just a habit you'll want to get into. So just as an example, plot the following points and then give me the rectangular coordinates. So we go 4 out, 1, 2, 3, 4, and then we go to pi over 2. I'm having trouble with the pen here. And that's the point 4 comma pi over 2 in polar. If I was to do it in rectangular, it would be 0, 4. So that just gives you an idea. Now you can have negative radians, degrees. You can have negative R values. For example, this one you would go negative 3 and then pi. Now I'm going to do this one the other way. Let's go to pi, and 3 would be here, but negative 3 takes us right back. This is negative 3 comma pi. You would say, or I would say, why don't you just call it 3, 0? And that's an interesting thing about polar. You can do it two different ways. In rectangular, it would just be 3, 0. Notice that would also be the same as polar. So it actually works. But that's just a coincidence. 16 and 5 pi over 6. And not to scale. 5 pi over 6 is here, so draw it out. And there we are. 16 5 pi over 6. And rectangular is a little bit trickier now, so we know that this is 30 degrees. So the x would be 16 cosine of 30 degrees, and the y would be 16 sine of 30 degrees. I'm going to write it down here just to leave myself some space going forward. And if you know those, you would say this is 8 root 3, right? And 8. Those are the two rectangular coordinate points if you know what you're doing. I want to check my work, make sure I didn't screw that up. Okay, yeah, no, I'm good. An important thing I forgot, you have to look at the diagram and be intelligent about how you label it. So it's out there in the second quadrant, so the x value's got to be negative. So forgot about that, but fixed it now. And one more. Already thinking the wrong way. Negative pi over 4 puts me here, but then negative root 2 puts me here. So this is negative root 2, negative pi over 4. This is 45 degrees. This is root 2 length, so the x is negative root 2 times cosine of 45 degrees. And the other one is just root 2. Again, I just have to look at it and say, what's going up? Sine of 45 degrees, which is root 2 over 2, basically negative 1 comma 1. So that's how we go from one way to the other. You can graph these. You can put them on your calculator, which I wasn't planning on doing, so I apologize. It's not up and running. You have to change your mode in your calculator, but definitely get handy at doing the calculator because it comes in incredibly useful to save you some time and aggravation. So mode, polar, got some nonsense in there, and we're graphing r equals 2. Well, it's just a circle with radius 2. Looks elliptical. Remember, this is not a square viewing window. Zoom 5 will give me a square if you really want to see it. Hey, look, nice circle, but not a big deal. Let's graph r equals -2. Let's not. You're going to get the same thing. Show it anyway. Same thing. Just starts at a different spot. Notice we're starting at 0 and pi, which is not as important as it is in parametric. You do have to know where the locations are. And let me rephrase that. It is pretty important. Now we want to graph theta equals pi over 6. Well, we can't because it is not an option. So we just say pi over 6. It's a line. All right, and we've dealt with graphing before. Throw it in your calculator. They, in general, in the AP exam, are not going to ask for a very challenging graph that you'd have to know how to do without a calculator. Polar coordinates is really built for a calculator. So let's take a look at these. First one was sine of 6 theta. Graph that, and we get something we can't even see. Zoom to enter. This is called a rose, and there are 1, 2, 3, 6, 9, 12 petals. So we have a rose, and I'm going to do this horribly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I have some follow-up on this in a little bit. We have something 1 minus 2 cosine of theta. And that is called a Limassol. And there's lots of different types of Limassols. Gotta watch out for these. You're gonna get one of these on the test, on the AP exam. And what makes it hard, besides the little squiggle at the bottom of the C, which I can never draw, and I could not get it to type, is you need to know this is where it starts at 0. Well, where is it at pi? Where is it at pi over 2? Where is it at 2 pi? Or it's back to the beginning. That's something you're going to have to learn to do. Get your calculator to graph more slowly and set the windows. For example, I want to know where it is at pi. I'll actually go window, just stop it at pi. And watch. It starts and it goes like that. Alright, so how about this point here? What is that? Looks like pi over 4. Let's see if that's accurate. I don't think it is. Graph it. Yeah, see, didn't even get that far. Maybe it's pi over 6, and so on and so on. So you have to figure all that out. And you have to play with the equation a little bit too. 4 sine of theta. Window, let's go to 2 pi, please. Thought it might reset for me. If I hit zoom 6, it would have. Alright, and that's a circle, even though, again, it looks elliptical. And you would have to play with this. If you're going to convert it over, you would say that, well, we'll come back to that. So how do we convert it to Cartesian? This is what I was about to say. So let's just get an example of that last one we had. R equals 4 sine of theta. Well, we know sine of theta is y over r. So r equals 4 times y over r. And I'm using this one down here. You need to memorize these. This is pretty easy. This is pretty easy. These are really not that complex to me. So we get r squared equals 4 minus y. Well, r squared is x squared plus y squared. Add the y over, equals 4. Complete the square. should get something like x squared plus, I feel like I've made a mistake in here. Yes, I did. I thought it was a minus y. It's a times y. R squared equals 4y. Knew something was wrong. X squared plus y squared. Let's subtract 4y. Equals 0 right now, but we'll complete the square. I did this recently. I'm not going to do it again. X squared plus y minus 2 squared equals 4. So it should be a circle of radius 2 centered at 0, 2. And it is, if you go back and look. My file is saving, taking its time. File's getting pretty big, so at some point it starts to have a little trouble with navigation. So this is at 0, 2, and the radius equals 2. And we just proved that down here. Anyway, so that's what I was doing here. Polar is just like parametric, as I mentioned earlier. Theta is the parameter. So x equals r cosine of theta, and y equals r sine of theta, or some function of theta, cosine of theta. X is always cosine, and y is always sine. So how are we going to find dy dx? We're finally actually getting into calculus. Well, just like parametric. We're going to do dy d theta over dx d theta. And that'll give us dy dx, assuming we don't put a 0 in down here. So let's find the slope of a polar curve. R equals 2 sine of 3 theta. X equals that function, 2 sine of 3 theta times cosine of theta. Y equals 2 sine of 3 theta times sine of theta. I've got to be careful with these dots because I just turned one into a subtraction a few minutes ago. And let's do it where theta equals pi over 6. So we take dy d theta over dx d theta, blast it out. Not in the mood to do it right now. Yeah, I'm going to end up getting dy d theta over dx d theta at pi over 6 is going to be equal to negative root 3. So how do we find the tangent line at pi over 6? Well, we plug it in to both of these, and we get x equals root 3 if we plug in and we get y equals 1. You can check those if you want. So tangent line will just be y minus 1 equals negative root 3 x minus root 3. Alright, that's very doable. It takes a little getting used to. It's not a big deal. The areas is a hassle. Mostly because we just can't quite envision how this curve works. I mean, you have to remember, and there's your formula, 1/2 r squared, or the function of theta. And you've got a curve out here. In polar, rather than doing this thing, delta x, we're going to do a wedge. And that's going to be our d theta as it goes to 0, so on and so on and so on. We can subtract. So we've got 2 of them, and the 1/2 r squared comes from the pi r squared formula. We don't have to worry about pi. That's going to pop up in the measurement of the limits. So the smaller loop of the Limassol r equals 2 cosine of theta plus 1. So again, in a test, you're probably going to be given this. Bear with me. What is it? 2 cosine theta plus 1. Skipped one of my notes. Interesting. 2 cosine of theta plus 1 graph. And we just want the little loop. Zoom. So we just want this area in here. And I'm going to change the window from -1 to 4. And I'd like to slow this down. I don't have that option. There it is, 0 step. .01. And up top, I'm going to say go to just pi over 2. Let's see where that takes us. We're going to use symmetry on these problems. Might have gone a little too slow. So pi starts out there, and pi over 2 is right there. It's actually good to know. Window. I keep doing my letters wrong. -1, enter. 5, enter. I was thinking of the other way around. And we'll make this 0.05, so hopefully it goes a little faster. Good. And let's start at pi over 2. Well, let's just go 0 to pi, see what happens. Find out where that is. Good. So, starting at pi and going to where? And I know this is tedious, but this is kind of the thing you're going to have to play with. Starting at pi and going to pi, 2 pi over 3 plus pi over 3. I'm going to try that and just see what happens. Probably should have tried pi over 6 first. Good. I've got half the loop, so we're just going to double whatever we get. And it's from pi to pi plus pi over 3, which is 4 pi over 3. So our limits and area equals integral from, 2 times the integral from, let's just do pi to 4 pi over 3. We could do 2 pi over 3 to 4 pi over 3. I don't think that's a good idea. It always seems to mess up with me. And it's the 2 cosine of theta plus 1 squared d theta. You can use your calculator, and probably should on this one. I've noticed that it really helps to have, these are going to cancel out, so I've just gotten rid of them. To have the formula for reducing a cosine squared to a half angle. And I'm not going to do all the integration. But this cosine squared theta is 1/2 plus cosine of 2 theta over 2. So, yeah. And that's handy to have because you're going to need it a lot. So 2 plus 2 cosine of 2 theta plus 4 cosine of theta plus 1, in case it shows up on the non-calculator portion of the test. So we should get approximately 0.544 when we're done. I warn that's challenging, and it is. There's a lot going on there, so give it a shot. How about the area between 2 curves? Just subtract them. Got to figure out which one's on the outside. Find the area that lies between inside the circle, r equals 1, and the cardioid 1 minus cosine of theta. By the way, cardioid is a type of Limassol, so I don't have to worry about that one too much. Here's r equals 1. Here's the Limassol, the cardioid, and they want this in the side of the circle and outside the cardioid. All right, this is very, 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 very challenging. First things first, we got to find our points like I showed you last time. Turns out for the cardioid, this is pi over 2. and that's 0. So here's my plan. I'm going to find the cardioid. This is not shown properly. I'm going to find the cardioid area. I'm going to subtract it from half the circle. I think it's the simplest, easiest way to do it. And again, I'm going to use symmetry. Area equals, you know what, let's show it how it's done for the whole thing. 2 times integral from 0 to pi over 2, 1/2 the outer circle minus the inner circle, which is 2.5 cancel, 1 squared, 1, minus 1 minus cosine of theta squared. As I mentioned earlier, you're going to need to have that formula handy because you're going to get things like this. You're going to want to sub in this for the cosine squared theta. So that you can integrate it. You should get something like, ones cancel, 2 cosine of theta minus 1/2 minus cosine of 2 theta over 2 d theta equals 2 sine of theta, pieces of cake, minus theta over 2, pieces of cake, minus, I gotta think, sine of 2 theta over 4, because 2, yeah, that'll cancel. And that's from 0 to pi over 2. Blast that out, you should get 2 minus pi over 4, approximately equal to 1.215. So that's tricky stuff. You got a bit of work ahead of you. Circles, already shown you. A sine of theta, a cosine of theta. The probably most important thing that's in here is the limits, because that'll help you figure out, how long it takes to get around the circle. You can graph slowly and see what goes on and play with it like I briefly showed you. You have a rose curve, which we showed you, and it's got all sorts of permutations. You could have 3 of them. Which is really, really horrible. Sometimes it goes 0 to pi, sometimes it goes 0 to 2 pi. You have to check it out. I got to do better than that. You'll have to do. You got Limassol curves, which are all over the map. They can be vertical, they can be horizontal, they could be cardioids. They have a loop. Get something like this. Keep forgetting to change colors here. And I'm not gonna lie, I thought that was a pretty good curve. So that's a Limassol with a loop. Notice I don't have the little tail on the Limassol up there. And I've shown you some of the other ones. I'm not going to go into them. There's dimple, there's convex, there's cardioid, and then lemniscate. A little trouble with the pronunciation. It's a little figure 8 curve. It can be up here. It could be here. Erase. So on and so on. So you have to get used to all of these. Do a couple more Limassols. This is the cardioid one. It actually almost looks like a heart, hence the name cardioid. And the dimpled one actually just never quite gets there. Looks like a heart, but it doesn't get all the way down. So it's a dimpled Limassol. Notice cardioid is a type of Limassol, so on and so on. So, got a lot going on. As I always like to say, happy mathing.